Our next speaker is Luiz Silva. He's a senior researcher based in the Institute for Environmental Engineering at ETH Zurich, Switzerland, where he leads the Eco-Hydraulics Research Group. Luiz has almost 2 decades of experience working on fish and hydropower, including fish passages, turbine mortality, and hydropeaking. And now Luiz will share some work on behavioral guidance systems and associated bypasses.
Good. So, yeah, thanks a lot, Abe, for the introduction. So I'm Luiz Silva. I'm currently based at ETH Zurich in Switzerland at the Institute for Environmental Engineering. And I've been working with fish passages in mainly tropical systems for about 18 years now, and dealing with a lot of different conditions and challenges. And currently, I will then take you into a journey of our current scenario in Switzerland, and specifically going to talk about bypass or the project related to advanced bypass systems for downstream migration of European key umbrella fish species, which is part of the PhD of one of our students that I'm going to mention at the end. So this work is being led by the Laboratory of Hydraulics, Hydrology and Glaciology at ETH in partnership with us at the Institute for Environmental Engineering. So that's the idealization of the future scenario until 2030 in Switzerland. So this beautiful landscape where you have hydropower plants installed, but at all of these plants you would have both upstream and downstream migration of fish freely through the river system. So that's the idealization scenario since the Swiss Water Protection Act has been put into force back in 2012, if I'm not mistaken. So based on that, we do have a lot of challenges in the system now, and that's what the Swiss Federal Office for the Environment is predicting, that both basically we need to restore river connectivity for fish movements. There are 7 species that have been defined as target species for upstream and downstream passage in the system. There are over 500 hydropower dams to be restored, where connectivity has to be restored. All fish, in the end, has been defined and considered that they need to move both upstream and downstream. They set a series of priorities for the construction and development of these upstream and downstream passage systems based on medium to long distance migrant fish species, and then looking to rivers with at least 1 migratory species. They set the deadline for the cantons back in 2014 to define which dams they would prioritize, and until 2030, all of them have to show efficiency. So that's the challenge that we are facing at the moment. With, for example, back in 2014, the beginning of these studies with bypass designs at Fawe to then define what type of downstream passage, downstream guidance systems with bypass would be installed. So you see that there was a mix of research at the beginning to inform decision-making plus a deadline to be met. So that's a very ambitious deadline that we are dealing with. Yeah, there we go. And one of the key points, in my opinion, and things that we've been working on is that, and that's, I believe, one of the key issues related to fish passage in the end is how we define target setting and monitoring goals for these different passages. So a demonstration of efficiency is then going into this big bucket of how we set efficiency, how we define target setting, what are the aims of the different fish passage at different locations. So based on that, we are dealing with a practical problem, but we dove into, okay, so if we think about downstream passage design, what are still the relevant scientific questions that we can incorporate into the practical information that we need to provide? And this then took us into this short review that is under development to look into bypass designs that have been studied. So there is a lot of information on that. We all know from different guidelines what are some of the parameters that are considered into these bypass design systems. Like if you look into the design, basically here, the design, the ratio of the bypass discharge by the ratio in the first bullet point there, by the ratio of the bypass discharge. Then you have it between 2 and 10% of the ratio that could be considered. Then if you go to another variable is the average approach or average flow velocity in the bypass itself that is set between 0.3 to 1.5 meters per second. And then the ratio between the bypass discharge and the approach discharge or approach velocity between 1 and 2. So this has been set in guidelines, but then when we look into practice and the recommendations that have been implemented, this is the number of studies that Max looked into, and then where they sit in terms of being present or in terms of the different variables that were considered for design. You can see that when we assume the ratio of the bypass discharge per the ratio of the total discharge at the dam, quite a lot of studies were implemented above what the guidelines define. So when we look at the bypass discharge velocity, also there's quite a lot of studies that were falling outside of what would be the threshold defined by the guidelines, as well as the ratio of bypass flow discharge by the total the approach velocity. So that showed, and when we put that into the context of what species have been studied, or what is the bypass efficiency, and if we focus on Potamodromus fish species, we can see that the bypass efficiency for Potamodromus fish species in a lot of cases is very low. So that set the question to us about, okay, what may be happening there? Is that a problem of the design? Is that a problem of the different variables? Like we can see that in nature, in reality, some of those values were falling outside of the thresholds that were set. Then we set out to investigate this a bit more in terms of looking at the bypass inlet gate and the different designs for these gates to see whether there is an influence of the bypass design gate into the passage efficiency for the bypass. We are doing that in reference to a pilot project in Switzerland, close to Geneva. And in that project, they are going to install a bypass at that red square over there. And that bypass is set out to have a top and bottom opening gate, which are approximately separated in the water column. You can see there that this is the water column of about 5 meters. The top gate would sit at about 1 meter below the surface, and the bottom gate would expand then from the bottom up to 1.5, 2 meters from the bottom. So taking that plant as a pilot study, we then moved to our flume at VW, at the Laboratory of Hydraulics, and we set up an experiment there to then test the bypass gate opening. So we have the flume here with the dimension of the flume. In the flume, we installed a bar rack, a fish guidance rack to then guide the fish to the bypass. And it's very important here to understand that we then assumed that the rack would have 100% because our focus was on the bypass inlet design. And therefore, in the bypass, we installed a screen to actually avoid fishing moving through the rack, and then all of the fish be guided to the bypass because, again, our aim was to understand the bypass design. So that's one assumption that you have to keep in mind. And then at the design, we put then a gate, and the gate is generally in there to reduce the discharge through the bypass and for operational reasons. And then we changed the gate with bottom opening or top opening and exposed different fish species through 3 or 6 different treatments. So we had the top opening with 3 different bypass ratios. We have the bottom opening with another 3 bypass ratios. And we tested barbel and trout in these settings. So we had about 4 weeks of testing, 8 replicates, 3 different groups, not going into the details of the methodology here, and we can discuss later on. We also conducted a series of hydraulic measurements to then model all of the different hydraulic scenarios to understand how the flow velocities were behaving. And we can see here from the bottom opening and the top opening approach that in the bottom opening, you see there's some circulation zone and then a high velocity through the bottom opening here. So you have increased velocities going through the bypass. In the top opening, that also increased the recirculation zone and also flow increase through the bypass. So here you can see on the left side, trout in the bottom opening condition, and you see that 2 passed and 1 will avoid, and strongly move upstream and try to avoid that increased velocity going through the bypass. And on the right side, you have also have barbel with the top opening. So it takes a while for them to move up and then get close to the increased velocities, 1 move, but you can see that there is a reluctance in the fish to accept that passage in the end. So based on that, with all of our experiments, we saw these bypass efficiencies for bottom opening and top opening, 3 on top, bottom opening, 3 on the bottom, top opening, trout on the left, barbel on the right. But most importantly here is to understand from some of our statistical analysis that trout had larger passage efficiency with the bottom opening design. So there was a significant effect of the opening on the passage with more trout accepting more of the bottom opening. And also there was a difference in species with trout having an overall passage efficiency higher than barbel in the end, which might be striking, right? Because you would expect that barbel would have a higher passage efficiency with the bottom opening inlet gate. So we also ran a survival analysis to understand the time for each one of these species to pass, and that was also significant with both with trout. For trout, it's more significant that you see the bottom opening with the purple color and the top opening with the green color, that they take longer to pass through the top opening and they pass faster through the bottom opening. Same with barbel, it takes much longer for them to pass, and the acceptance was much lower. So to conclude, we saw that basically with these flow velocity, as the flow velocity increased sharply at top and bottom openings of the bypass, trout and barbel often showed an avoidance behavior to the high velocity gradients. The preferred hydraulic conditions are species-specific, as we saw as well. Overall, trout showed higher and faster bypass acceptance or efficiency compared to barbel, and which highlights the need for us to indeed understand more of the behavior and the response of these fish to these different designs before we set out to implement all of these designs at different locations. With that, I would like to thank all of the partners in the project, funding that came from the Swiss Federal Office of Energy. Max is a PhD student working and leading these experiments, co-supervised by myself and Ismail and Professor Robert Bose from the Hydraulics Institute. Thanks a lot, and with that, I'll take any questions.